Hello, this is Dr. Armand bringing you another exciting lecture on in chemistry. Today we'll be talking about titrations. So what are the different types of titrations? What do their titration curves look like? What are the principal species at different points in the titration? And how to do calculations for some of the titrations. And there are three main titrations: a strong acid, strong base, weak acid, strong base, and weak base, strong acid. We'll also touch on polyprotic acids and briefly mention amino acids as well. So sit back, relax, and enjoy the show. And so we'll be discussing today, I should say, uh, different components of titrations and calculations involving titrations. Now, one thing with titrations is when we do an acid-base titration, the most common way to perform an acid-base titration is using a pH meter. And from the pH meter, you can determine what the pH is as acid or base is added to your solution. And then what you would do is you would take a plot of this pH and volume of base or acid, which is called the titrant, and then from there you get your acid-base titration curve. Now, a quicker way or less precise way of doing a titration is by using an acid-base indicator. And so an acid-base indicator is a weak organic acid, which will denote as HIN, and a conjugate base, which is denoted IN minus. And what happens is for the weak organic acid, its color differs from the color of the conjugate base. So for example, the acid could be yellow, the base could be blue. And it changes over a specific pH range. And so the way this works is a Le Chatelier's principle. So you have an indicator with color A, say it's red, and you have its weak acid of the indicator is color red, and the weak base is color blue, for example. And so as you add more hydroxide, the hydronium ion decreases because you're reacting with the product, you're removing product. So it shifts the reaction to the right and makes more product, which over time will cause the solution to turn blue. So that's what happens when you add a strong base. It reacts with the weak acid, it pushes it to the right, making more of the blue color in this example, and so your solution turns blue. Now, if it were the opposite, say we're adding a strong acid increases the amount of H3O plus, causing it to shift to the left, and that makes the solution become more red. And this is how an indicator works. And there are many different types of indicators. It depends on what we refer to as the endpoint. Endpoint is the pH at which the indicator changes color. Now, the endpoint must coincide with what's called the equivalence point of an acid-base reaction. And we'll talk more about what's the pH of equivalence points of different types of acid-base reactions. But this is the pH at which the moles of acid equal moles of base. And notice that it's moles, not molarity, not mass, not volume. And so what you want to do is you want to pick an indicator whose endpoint coincides with your equivalence point. And that's the key thing. So when you look at indicators, you want to see, okay, where does it change color? That's where I want to, and then you want to look at your acid-base reaction. Where will the equivalence point be? And you want to pick an indicator that changes color at around the same pH as your equivalence point. So some common ones, for example, where's one? Bromothymol blue is what we use in Gen Chem 1 lab. So in a basic pH above 7, it's blue. At around 7, it's green. And then when it's below 7, 6.8, it turns yellow. So it has distinct pHs. And this would be good for a strong acid, strong base titration. Because as we'll see in a little bit, for a strong acid, strong base titration, the equivalence point is always 7. So a strong acid, strong base titration would be pH 7 equivalence point. So you would want to get an indicator maybe such as bromothymol blue that turns green around 7. Another common one is phenolphthalein. Phenolphthalein is colorless at very acidic pHs, and it turns pink around a pH of 8.5 to 9. So you would want to choose this indicator if you were doing an acid-base reaction whose equivalence point is around pH 9. Well, you know, around 8.5 to pH 9. And this is probably really good to use if you're doing a weak acid and a strong base, such as acetic acid and sodium hydroxide. Now, these are just some, but all of them have different endpoints. So the endpoint is the pH at which the indicator changes color. Equivalence point is the pH at which the moles of acid equal moles of base. So these are two different things, but you want the pH of each to coincide together. So if you're going to titrate a strong acid and a strong base, maybe you want to pick bromothymol blue. If you're titrating a weak acid and a strong base, maybe you want to pick phenolphthalein. But the endpoint and equivalence point are two different independent properties. They're not together. And so with that said, we're going to start talking about the different types of titrations. And so the first type of titration is a strong acid, strong base titration. So you titrate a strong acid with a strong base, or you titrate a strong base with a strong acid. And so the equivalence point, again, is where the moles of acid and base are equal. So we're talking about moles here. And for a strong acid, strong base, the pH is always 7. Again, as I said, the endpoint is where the indicator changes color. Now for this strong acid, strong base titration, you see it starts increasing slightly, and then it hits a dramatic rise, and then it levels off. And so this dramatic rise, the midpoint between where it starts going up and starts coming down, that's the equivalence point. And so here you see the equivalence point is pH of 7. So why is the equivalence point of pH of 7? Is because at that pH, the only species you have in solution are water, sodium ions, and chloride ions. Since sodium ions and chloride ions are neutral species, that's why you have a neutral pH. Before the equivalence point, you have a combination of chloride ions, sodium ions, water, and hydronium ions. Makes it acidic. At the initial pH, you have hydronium ions and chloride ions, which makes it acidic. Now, above the equivalence point, you see the only things in solution are hydroxide, sodium ions, and chloride ions. And so the only equation you need for a strong acid, strong base titration is this one right here. pH equals a negative log of hydronium ions. And so since we're titrating a strong acid with a strong base, you know it's a strong acid because we start at a very low pH and it increases over time. So now we're going to look at some calculations involving strong acid, strong base titrations. Again, this is the only equation we're going to use. pH equals negative log of hydronium ion. So here we have a problem. We want to calculate the pH during the titration of 40 milliliters of hydrochloric acid with, or 0.1 molar hydrochloric acid with 0.1 molar sodium hydroxide. And so we want to ask, what's the pH before we add any sodium hydroxide after 25 milliliters, after 40 milliliters, after 50 milliliters. And so if for 0 milliliters, all you do is you take the concentration of the acid, you take the negative log of it. So negative log of 0.1 equals 1. So the initial pH is 1. Now we want to know what's the pH after 25 milliliters of sodium hydroxide has been added. So what we want to do first, we want to calculate the moles of H3O plus, which is equal to the moles of HCl. And that equals 0.1 times 0.04. So this is the moles of acid or H3O plus we have. We're going to be using that quite often, so we're going to keep it up here. Now we need to find the moles of hydroxide. So we're using 0.1 times 0.025. And that's the moles of hydroxide at 25 milliliters. So now we're going to be using this equation. And so all the hydroxide is going to react with H plus to produce H2O. So we're going to need our little modified ice table. So initially we start with 0.004 moles of H plus, 0.0025 moles of hydroxide. You always subtract the lesser one from the greater one. So we're going to subtract 0.0025 moles of hydroxide from H plus. H plus is the same as H3O plus. And so we get 0.0015 moles of H plus left over. So now we need to find the new concentration of H3O plus. Now we got to divide it by the new volume. So the total volume equals 40 plus 25. 65 milliliters. So that's what we divide the new moles by. We divide it by the new volume. Make sure you convert it into liters. And that's the new concentration of acid. Then we take the negative log. So pH equals negative log of 0.0231. 1.64. So we went from a pH of 1 to a pH of 1.64. Again, H plus is the same thing as hydronium ion. Now we go to C. So we want to know what's the pH after 40 milliliters of base has been added. So here we want to determine the moles of hydroxide. So it's 0.1 times 0.04 equals 0.004. And so you notice here that the moles of hydroxide equal the moles of hydronium ion. So this means that we're at the equivalence point. And since we're at the equivalence point, there's no calculation to be done because the pH is 7. So now we're at a pH of 7. So whenever you're at the equivalence point for a strong acid, strong base titration, you just put pH 7. No calculation needs to be done. Now we want to know the pH after we've added 50 milliliters. So let's come over here, determine the moles of hydroxide. So we have 0.005 moles of hydroxide. Now we need this. So we're going to have our initial change end. So initially we started with 0.004 of H plus, 0.005 of OH minus. Now notice here that the OH minus is greater than the H plus, so we're going to subtract the H plus from both. So here we have an excess of OH minus, so we're beyond the equivalence point. So now we know the moles of hydroxide now. We need to find the new volume. It's 50 plus 40. And now we can find the new concentration of hydroxide. Now we find a new concentration of hydroxide, we can find the POH. and then the pH. And then pH. Is 12.04. And these are all the calculations you do for a strong acid, strong base titration. Initial pH, very easy. Just take the negative log of the original concentration of the acid. Then after that, you find the moles of base. If the moles of base are less than the moles of acid, you subtract, find the new concentration of hydronium ions, and then find the pH. If you're at the equivalence point, very easy. pH is 7. Moles of base equal moles of acid. And if you're beyond the equivalence point, your hydroxide is going to be greater than the H+. So you'll find the moles of hydroxide and then find the concentration of hydroxide, find the POH and pH. Same calculations you do for a strong acid, strong base titration. Look at one more. So here we have 75 milliliters of a 0.35 molar HClO4 solution is titrated with 0.55 molar KOH. What's the pH after 50 milliliters of KOH has been added? So this is the equation. H plus OH minus gives H2O. Let's find the moles of acid or moles of H3O plus. Zero point 0.0263. Now we do the same thing with hydroxide. Moles of hydroxide equal moles of KOH equals initial change equilibrium, or ends, not equilibrium. Now notice here the moles of base are greater than the moles of acid, so we're going to subtract the moles of acid from the base. So now we see we know what the moles of hydroxide are. We need to find the new total volume of solution. Then we can find the new concentration of hydroxide. Now we can find the pH, or excuse me, POH. and then the pH. That's the pH of this solution. Again, negative log of hydronium ion, negative log of hydroxide is the only calculation you need to use. So that's strong acid, strong base. Now we're moving on to weak acid, strong base. So in a weak acid, strong base, you're forming as a product, you're forming a weak conjugate base. So for a weak acid, strong base, the equivalence point is always above 7. Because again, in a weak acid, strong base titration, you're forming weak conjugate base. And so this is what the pH or the titration curve of a weak acid, strong base looks like on here on the right. So again, we have our initial pH. At the initial pH, you just calculate the pH of weak acid, strong base titration initially, just like you would a weak acid like we learned in the previous chapter. So you write the equilibrium, you determine, HA, A minus, H3O plus, just like we did in the previous chapter. You do it there because the main species is just a weak acid. Now between the initial pH and the equivalence point, we're going to be using the Henderson-Hasselbalch equation because again, you're in the region that's called the buffer region. So the buffer region contains weak acid, weak base, and a few other counter ions in solution. So there's where we use the Henderson-Hasselbalch equation. At the equivalence point, the only thing in solution is the conjugate base with a few other counter ions or sodium ions and water. So here we have to determine the pH of a weak base, just like we did in the previous chapter. Now above the equivalence point, the main species is hydroxide in addition to some weak base and sodium ions. And so there you just need to find the hydroxide ion concentration, take the negative log of the hydroxide to get the POH and then the pH. So again, initially, you're just finding the pH of weak acid, just like was done in the previous chapter. The buffer region, we use Henderson-Hasselbalch equation. Equivalence point, we're solving for the pH of a weak base solution, and then above the equivalence point is just determining the hydroxide ion concentration and finding the pH that way. Now, one important point in this titration curve is the volume is half the volume of the equivalence point. And this is where the concentration of HA equals the concentration of A minus, which means pH equals pKa. Because of the concentration of weak base and acid are the same, the log of 1 is 0, the pH equals the pKa. And this can be used if you're ever wanting to determine the identity of an unknown acid, unknown weak acid, you could titrate it, find the equivalence point at half the volume of the equivalence point, determine the pKa, and then you can determine the identity of the acid. And so in this type of titration, there are 4 distinct regions: the initial region, the buffer region, equivalence point region, and beyond the equivalence point. They're all going to use different equations to calculate the pH. So this problem I've divided up into 5 parts or 4 parts because they take a long time. So here we want to know what's the titration. We want to titrate 30 milliliters of 0.1 molar benzoic acid with 0.15 molar sodium hydroxide. Calculate the initial pH before the titration begins. So we're just going to be doing like we learned in the previous chapter, the dissociation of your weak acid, find the hydronium ion concentration, and then we can find the pH. So initial, we have 0.1 molar. 0, 0. Change, minus X, plus X. This should be very familiar. Plus X. Equilibrium. One minus X plus X plus X. Now look here, the concentration of benzoic acid is a lot greater than the Ka by a factor of 10 to the fourth. So we can disregard the minus X here. So then we get 6.3 e to the negative 5 equals x squared divided by 0.1. So x squared equals 6.3 e to the negative 6. Now we take the square root. So x equals 2.51 e to the negative 3, which equals the hydronium ion concentration. Now we can find the pH. We get the pH is 2.6. And so that's the initial pH of this benzoic acid solution. Nothing new here. Now we want to know what's the pH after we've added 12 milliliters of the base. And so now what we need to do is we need to find out the moles of acid which is going to be equal to the moles of benzoic acid. So it'd be 0.1 times 0.03 equals 0.003. And we want to know the moles of strong base. So now we found the moles of acid, moles of base. Just like a buffer solution, since we're reacting a strong base with a weak acid, we've got to see how much weak acid is left over. So initial change. Since the base is less, we're going to subtract the base from the acid. If the base was more, that tells you you're outside the buffer region. Then we have equilibrium, or ends of the reaction. Now we need to find the new concentration of acid and base. So we need to divide it by the total volume. (30 plus 12). And we find the concentration of weak base. Now we can use the Henderson-Hasselbalch equation, because up here I calculated the pKa, which is shown there, 4.2. So now we know that pH equals 4.2 plus log of base divided by weak acid. And we're at 4.38 is the pH. And this is how you calculate the pH of a weak acid strong base titration in the buffer region. So again, this is the initial pH. This is the buffer region. So, moving on. So now we want to calculate the pH at the equivalence point. So first what we need to do is we need to calculate the moles of acid and moles of base. And again, I do this the long way, but if you do it a short way, that's fine. I'm just doing it so everyone can see all the steps. And so if we're at the equivalence point, the moles of acid equal the moles of base. So then the moles of base are also but we need to find out how much hydroxide was used, what volume of hydroxide was used to get 0.03003 moles. So volume of hydroxide equals 0.003 divided by 0.15. (20 milliliters). So our total volume is 30 plus 20, 50 milliliters. So again, we have a weak acid, strong base. Let's do the modified ice. change. Again, this is at the equivalence point. At the end, so now we need to find the concentration of weak base. So that's the concentration of weak base, but we're not finished yet. Now we need to calculate the pH of a weak base solution. So we're going to use the same thing that we used back in the last chapter. So again, this is equilibrium. Just like we used to calculate the pH of a weak base solution in the last chapter, we're going to do the same thing here. So one thing we're missing is the pKb. And so if we have the pKa is 4.2, the pKb is just 14 minus that, and then we can find the Kb, which is 1.58 times 10 negative 10. So we're going to need this in order to determine the hydroxide ion concentration. So again, we have our initial, and then we have our change minus x plus x plus x, and then we have our ending. Oop, that looked bad. Let me undo that. So notice here that the Kb is a lot smaller than the initial concentration of 0.06, so we can negate that. And so then we get 1.58 e to the negative 10 equals x squared divided by 0.06. X squared equals 9.48 e to the negative 12. And then x equals 3.08 e to the negative 6. And again, this is the hydroxide ion concentration. All right. Now we can find the POH. .51, and then we can find the pH. Which would be 8.41. 8.49, my bad. And so you have to do all of this to calculate the pH at the equivalence point. And notice that it's above 7. So anytime you calculate the pH at the equivalence point for a weak acid, strong base, it should always be greater than 7. This is how you calculate the pH of a weak acid strong base solution at the equivalence point. Now we want to know what's the pH after we've added 22 milliliters of base. So again, we need to find out the moles of base and the moles of weak acid. Moles of strong base. Let's go ahead and find the total volume. All right. So we'll be using this equation. So notice here that the moles of weak acid is less than strong base, so we're subtracting the moles of weak acid from strong base. Equilibrium. So notice that we have moles of strong base left over, so we're going to find the concentration of hydroxide, and then we can find the pH. So that's the concentration of strong base. Now we can find the pOH. .24, and then we can find the pH. 11.76. This is how you calculate the pH after equivalence point. For a weak acid strong base. So one more example here, and then we'll move on. We want, again, we're titrating 20 milliliters of 0.2 molar hypobromous solution with 0.1 molar sodium hydroxide. What's the pH before any base is added? Before any base is added, before any base is added, let's see, we're going to need this HBrO plus H2O BrO minus, and H3O plus. So we're going to calculate the pH of a weak base solution. So initially, 0.2 molar, 0, 0, 0. Change, minus X, plus X, plus X. Now again, I shouldn't have put 0 here. Let me mark that out. There we go. At equilibrium, so again, the Ka is a lot smaller than the initial concentration, so we can disregard the minus X. And so we get 2.3 e to the negative 9 equals X squared divided by 0.2. So X squared equals 4.6 e to the negative 10. X equals 0. Then we can find the pH. That's the initial pH of this buffer, of this 0.2 molar hypobromous solution. So we want to know what's the pH when the concentration of HBRO equals BRO minus. And so what we have to remember is that here where we're in the buffer region, pH equals pKa plus log of concentration of base divided by concentration of acid. And since these concentrations are equal, they cancel out. And the log of 1 is 0, so pH equals the pKa, and the pKa is 8.64. pH equals pKa, which equals 8.64. And so that's the pH when the concentration of weak acid equals the concentration of weak base. Now, what's the amount when the amount of hydroxides added is twice the amount of HBRO present? Initially, what's the pH? So again, we have our moles of acid. Moles of acid is 0.2 times 0.02. Moles of hydroxide are going to be double this. It's going to be 0.08. So what's the volume of hydroxide needed for this? (800 milliliters). Whew. That's a lot. Let's double the concentration. Yeah, I could see that. Total volume. Oh, my bad. I missed a 0. My bad. I was like 800. That's a lot. It's 80. Yeah, 80. Whew. I was like, wow. That's 80. That's 100. A lot better. So now we set up this. Again, I'm doing it the long way. I mean, I'm sure there's shortcuts you can take, but I like to do it the long way so you can see everything, the mechanics, as they say. Again, the weak acid is less than the strong base, so we're going to subtract from that. So now we have moles of hydroxide. We can find the concentration of hydroxide. So now we have the concentration of hydroxide. We can find the POH and then the pH. And then we can find the pH. Oops, I didn't even work it out. 1.40. And then pH 14 minus 1.40 equals 12.6. So that's the pH when you add double the amount of moles of strong base. All right. So that was calculations involving strong acid, strong base titration, weak acid, strong base titration. We're just going to talk about the other types of titrations, no calculations. So for a weak base, strong acid titration, again, everything is backwards from what we did in the previous one. So at the initial pH, you're going to calculate the pH of a weak base solution. And again, this is because the only thing in solution is your weak base. So you calculate the pH of weak base solution initially. Then you also have a buffer region between the initial pH and the equivalence point. But notice here, when we're dealing with a weak base, strong acid titration, it produces weak acid. So since it produces weak acid, the equivalence point is always going to be less than 7. So equivalence point is always below 7 because it produces, this reaction produces a weak acid. So between the initial pH and the equivalence point, let me put it right there, you're going to use the Henderson-Hasselbalch equation, HH equation. at the equivalence point, you're just going to have weak acid. So you got to calculate the pH of a weak acid solution. And look, see, the equivalence point is less than 7 because you're producing a weak acid. At the equivalence point, there's only weak acid and anion in solution. In the buffer region, we have weak base and its conjugate acid in solution along with chloride. Now below the equivalence point, you have an excess of hydronium ions, so then you just calculate the pH of pH using negative log of hydronium ion. So again, it has 4 regions, and you calculate using different equations based on which region it's in. So again, at the initial pH, for weak base, strong acid titration, there's just weak base. In the buffer region, we have a combination of weak base and weak acid. Notice that when the concentration of weak acid equals weak base, the pH equals to pKa, and this is at 1/2 the volume of the equivalence point. So you can use this to identify the acid or the compound. They actually do this. Then in the equivalence point, there's only weak acid and some counter anions. So only NH4 plus is present in this example. Beyond the equivalence point, we do have some counter ions, ammonium, chloride, but we also have hydronium in excess. So then we use pH equals negative log of hydronium ion. And for a weak acid, weak base, strong acid titration, methyl red is an ideal indicator because it's yellow in a basic solution and turns red or orange red in an acidic solution around the equivalence point of this acid-base reaction. So here, for example, we have a solution of trimethylamine and is titrated with hydrobromic acid. So we have trimethylamine, a weak base. So we have a weak base and a strong acid. And it wants to know what's the major species present at the equivalence point. So remember, if we're having a weak acid and a weak base and a strong acid, what's being produced is the weak acid and anions. So let's look at this. So we have CH3, CH2, 3N plus HBr. And this should be a 3 here. It's trimethylamine. And so we produce CH3, CH2, 3NH plus Br minus. And so at the equivalence point, you're only going to have these 2 species present. The anion of the strong acid and the protonated weak base, so the conjugate acid of the weak base. So what's in solution? That would be Br minus and made some boo-boos. This should be a 3 here. This should be a 3 and a 3. Let's see, erase this, make this better. 3. Oh, undo. Nope, undo. And so the species in present are B and F at the equivalence point. And then just to finally conclude with polyprotic acids. So these are di and triprotic acids. Each proton has its own equivalence point. So for a diprotic acid, you have 2 humps. So 1, oops, go back. Yep. So here we have 1 equivalence point for the first proton, and then we have the second equivalence point. And so as you see, as you go from 1 equivalence point, the first one to the second one, you go from 1 buffer region to the next buffer region. But above this, you have an excess of OH minus. So only when you're above the second equivalence point, you would need to just, there's where you would only have an excess OH minus. Now the second equivalence point, since the only thing present is a weak base, you would have to calculate this using, you would calculate a weak base solution. Now here, when you're at the equivalence point, since HSO3 minus is a weak acid, you can calculate that pH like you would for a weak acid. Or actually, yeah. Because there's only HSO3 present. It's the weak base. So use its KB. I guess you could calculate it as I want to go with weak base because there's only weak base left, but then also it turns into the weak acid. So I don't know if it's weak base or weak acid. I'd have to double check that. But you would calculate the pH as if it was just a weak base solution or a weak acid solution. So if you use the weak acid, then you could determine, let me see if I can figure this out. Let's see. So the equivalence point, the first one is 40 milliliters. 40 and 40 is 80. I'm working this out for, give 1 second. 0.04 divided by 0.08. So that is the concentration of HSO3 minus. Okay. Okay, let me write that down. PKP1. Times 0.05, second square root, second answer. Negative log of second answer. 14 minus 1.85. Log negative answer. I guess you'd have to calculate it as a weak acid. I'm going to have to look into that. Let me delete this for now. .24. For right now, it's either calculated as a pH of weak base or weak acid. I'd have to look into it for next time. I'll double check, but let me just erase it for now. But at the equivalence points, either you're going to calculate the pH as a weak base or as a weak acid. But we're not going to do any calculations involving polyprotic acids. What you should remember is that for a diprotic acid, it has 2 humps or 2 equivalence points. For a triprotic acid, it has 1 or 3 equivalence points. So diprotic, 2 equivalence points. Triprotic, 3 equivalence points. And then lastly, just to mention about amino acids, which are biological polyprotic acids. And the interesting thing about amino acids is they can be Zwitter ions. So Zwitter ions means that it has a positive charge and a negative charge. So at a very low pH, you see here that both the oxygen, the OH, the oxygen, the OH group is protonated, and also we have a protonated amine, NH3. So the oxygen is protonated, the amine is protonated, so this gives the nitrogen a positive charge at a very low pH. When we add 1 mole of hydroxide, you see that the first proton to come off is the proton on the carboxylic acid. And the reason why this is a easier proton to remove because it's on a more electronegative element. And so when an amino acid is at a neutral pH, it's called a Zwitter ion, meaning it has a negative charge and a positive charge in the same molecule. So the positive charge is on the nitrogen because it has 4 bonds, and the negative charge is on the oxygen because it lost its proton. So at a neutral pH, amino acids have what are called Zwitter ions. They have a positive and negative charge in the same molecule. Now, if you add enough base, you see you can remove that extra proton on nitrogen so that now you have an unprotonated, fully unprotonated amino acid at high pH. So at high pH, it's fully unprotonated. At low pH, it's protonated. At neutral, only half of it is unprotonated. That's the hydrogen on the carboxylic acid group to form the carboxylate. And so biological polyprotic acids would have 2 humps as well. So if we were to draw the titration curve. It would look something like that. And so again, the first titration, the first equivalence point here would be with the hydrogen, the acidic proton on the oxygen. The second titration point here would be due to the acidic proton on the nitrogen. Acidic H plus on oxygen. Acidic H plus on nitrogen. And so, sorry, I apologize for getting stuck on the previous polyprotic acids, but I'll look into that and maybe post an updated lecture of that later. But that concludes today's lecture over, nope, exit, nope, the, oops, I don't know what's happened. That concludes today's lecture over what is, it's actually doing my text. That's pretty wacky. So again, that concludes today's lecture over what is a titration curve, what are the different types of titration curves. So there are three main, or actually, well, three main categories of titration curves. These include strong acid, strong base, where the equivalence point is pH 7. Weak acid, strong base, where the equivalence point is greater than pH 7. We looked at weak base, strong acid titration curves, where the pH at the equivalence point is less than 7. We looked at calculations involving strong acid, strong base titrations, and also weak acid, strong base titrations. So that's all for today. Hope you enjoyed the lecture. We'll see you next time.